Hey, good morning, guys. I hope you're doing well. So, not a lot left to talk about. We have actually two more topics that we're going to be talking about. One is entropy, which is what we're going to be talking about today, and then we have free energy. Now, I'm going to warn you, today's lecture is extremely short. So, because there's not a lot about entropy that we need to talk about. So, it is possible that we could do both of those lectures today if you wanted to do so. And what that would mean is that next, for the rest of this week, we wouldn't have to meet. So we would not have to meet again. You could then use the rest of your time preparing for the next exam and for the final. If you have anything that you want to talk to me about between now and then, absolutely, I'm more than willing to meet with you. So that's entirely up to you guys. So when we get done with today's lecture, we'll talk about that again. I just wanted to throw that out there so you guys could think about it. Do you guys have any questions about anything so far? I will say I'm not quite done with the exams yet, but they will get posted this afternoon. So they didn't look weird or strange or anything like that, so I'm not concerned about it. So. Okay, then I'm going to go ahead and start talking about entropy. So, when we talk about entropy, there are a couple of things that we need to talk about. The first of which is the three laws of thermodynamics, which we haven't talked about yet. We'll then talk about spontaneous processes a little bit more than we have done in the past. We'll talk about entropy, and then we'll talk specifically about the second law of thermodynamics in more detail. Okay? This is all from chapter 17. So when we talk about our laws of thermodynamics, the first law of thermodynamics states that energy cannot be created or destroyed. We've talked about this in the past. We've said that we have to take energy from somewhere to go somewhere. We don't talk about it as much in chemistry as we do in physics, but it is something that exists in both places. So when we talked about redox, we had to have electrons come from somewhere to go somewhere else. Okay, so that's part of where that comes from. The second law of thermodynamics says, for a spontaneous process, entropy of the universe increases. And we'll talk about that in more detail in a little bit. The third law of thermodynamics states that a perfect crystal at 0 Kelvin has 0 entropy. Now, what do I mean by entropy? Well, we'll get to that in just a second, but that's a term that we use. All right. When we talk about a spontaneous process, the way that we've talked about that in the past is to say a process that happens without any intervention, that will not undo itself in nature without intervention. So things that happen spontaneously, if I hit a window, it breaks, it shatters into a bunch of pieces, that window is not going to remake itself without a bunch of intervention from the outside. So somebody putting all the pieces back together, gluing it, somehow making it one piece again. Okay, so that's the kind of thing that we're talking about. If it's spontaneous in one direction, it is not spontaneous in the other direction. Okay, that is by definition true. So while it can happen in both directions, and it often does, it is only spontaneous in one direction. Okay. Now, what determines if a reaction is spontaneous? Well, there's a number of things, and we've talked about the enthalpy part of this. So we talked about whether or not the energy is being put in or taken out of that system. So generally speaking, exothermic reactions, those that give off energy to their surroundings, are more spontaneous than endothermic ones. Okay, but that's not always the case. Okay, so it's not simply something that's related to that thermal energy. It's not always about that. So while it's generally speaking more true that if something gives off energy to the surroundings, that's spontaneous, that is not always the case. Okay. Now, a change in order is another thing that we have to be able to talk about. Okay. So entropy is a measure of how spread out or dispersed the energy of a system is among all the different possible ways that system can contain energy. Okay. So the greater the dispersal, the greater the entropy. Entropy is a way of measuring the disorder of a system, how random that system is, that the more random it is, the more favorable it is. And that is a better entropy state. Now, I know that doesn't sound like a very, satisfactory definition. It didn't sound like one to me. So I went, okay, fine, let's go find a better definition. Thermodynamics states that a measure of the unavailable energy in a closed thermodynamic system that is also usually considered to be a measure of the system's disorder. It is a property of the system's state and that varies directly with any reversible change in heat in the system and inversely with the temperature of the system. Sounds like a bunch of mumbo jumbo to me. So that didn't help me very much. Like I said, entropy is a measure of the disorder. So there are a couple of different ways that we can think about this. We can think about this in terms of phase. Something in the gas phase is way more disordered than it is in the liquid phase because there are simply more places that it can exist. It has more randomness because of the movements, because in the gas phase, it moves more than it does in the liquid phase. So that's a more disordered system. A system that has more molecules has more disorder in it because there are more places the electrons and the nuclei can exist. So the bigger it is, the more disorder it has. Okay, so something that's very, very small has less disorder than something that's very large. And that's just because of the number of electrons that are in it. Okay, so that's another thing that we have to be able to talk about. One other thing that we can talk about is how ordered that state is. So like I said, gas phases, not very ordered, very disordered by their nature. Liquid phases are more ordered, but not ridiculously so. A solid phase is very ordered, But if it has an impurity in it, then there is inherent disorder within that salt. Okay, so if I have frozen ice, but there's something in that ice, color particles, sugar particles, anything like that, then there is some disorder within that. Okay, so that disorder is part of the measure that we're looking at. And the very presence of that impurity will lead to disorder. Okay, so there are a lot of things that are involved in this disorder that we're talking about. It's generally speaking a way that we talk about any energy that's present that cannot be used to do meaningful work. Okay, so when we talked about meaningful work, if we can't convert that energy into meaningful work, then it's something that we consider in the entropy. Okay. So any questions on what we mean by entropy? It's a very nebulous term that has that in my mind is completely equal to disorder. Okay. Now, when we talk about entropy, it is possible to measure the absolute entropy. So there is a lower level against which we measure everything. Standard entropy is the absolute entropy of a substance at 1 atmosphere, and usually quoted at its value at 25 degrees C for 1 mole of substance. That's what we're talking about when we talk about that standard value. So that little circle that goes with it can be listed as either joules per Kelvin or joules per Kelvin mole, but the value is assumed for 1 mole of substance. Okay, so no matter which way it's tabulated, we're assuming it's for 1 mole. Okay. Entropies of elements and compounds are all positive. Everything is positive. All right. More complex molecules have higher entropy values, and again, that's because there are simply more places that those electrons can exist, the nuclei can exist. Gases are less ordered than liquids, so that means the entropy values are higher for gases than for liquids, and again, for solids. Heavier atoms have a higher entropy because there are more ways to organize the nuclei and electrons in larger atoms. Okay? So hopefully that helps. I mean, I talked about most of that, but hopefully that helps. Okay? And remember that these are all measured in joules. What we talked about when we talked about enthalpies were kilojoules. So those are not the same exact units. They're the same kind of units, but not the same size. So we've got to be aware of them. Okay? Now, the second law of thermodynamics states that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So, for the universe, for everything in total, that always increases for a spontaneous process. And that's a combination of the system and the surroundings. Okay, so whatever system we've defined, this little thing that we're looking at, plus everything around it. Okay, so those two must increase in a spontaneous process. That does not mean that the system increases, but it does mean that the combination of the two has to. For an equilibrium process, it remains unchanged. So whatever it was at the time, and actually it's not equal to 0. It's whatever it was at the beginning, it's going to stay throughout that process. Okay, it's going to be greater than 0, but it will not change. Okay, so if the delta S, which was what we call entropy, so S is for entropy, so the change in entropy for the system is negative. The process is not spontaneous in the direction described. Okay, it is spontaneous in the opposite direction. All right, so we can have processes that are not spontaneous in the direction that they're described, but the combination between the system and the surroundings will give us a way that it can go. Okay. Now, that entropy change for the system is calculated exactly the same way that we did for the enthalpy, except instead of H, we use S. Okay, so H was for enthalpy, S is for entropy. So remember, H is my enthalpy, S is my entropy. This is my heat, and this is my disorder. And it's always the same thing. So we calculate that change for that particular thing. If we're calculating, delta H formation for this, that delta S at standard conditions for formation of that material will be equal to the sum of the component, the number of components, the number of moles, times the delta S for formation of my products minus the sum of the number of moles times the delta S of formation for my reactants. So, same equation that we talked about for enthalpy, exactly the same equation. But instead of talking about the enthalpy values, we're now talking about the entropy values. Now you'll notice that I say this is not on the exam handouts. If you look at the exam handouts and you look at that table that's presented, you will not find this anywhere here. And the reason for that is because I chose one equation from both semesters, 110 being the ideal gas law and 111 being this equation right here that you guys would need to know, because it's the most important thing that we learn this term is how to calculate these things. And because they're all done exactly the same way, I didn't figure you needed a reminder of what that looked like. So that's why it's not included. So you will need to know that reaction, that equation. So that one you don't get. So this equation right here, you will need to know. The biggest thing that I see people miss is to multiply by the number of moles. And again, if you're watching the units and you know that this is an entropy per mole, then you need to multiply by the number of moles to calculate it for whatever you're looking for. Now it said here on the slide that the standard entropy values were given on the exam handouts, but I have taken them off. So any value that you need will be found somewhere on the test. It may not be in the exact question that you're looking at, but there will be a table somewhere that contains those values. So remember to look for that you're somewhere on the test. So if we're talking about the same thing multiple times, there will be a table on the test that has that value that you may not see every single time we talk about that material. Okay. Things that are common for that, just values for oxygen, hydrogen, those often occur multiple times. So those are things that would be in a table as opposed to distributed each time they were needed. Okay. Now, if a reaction produces more molecules of gas than it consumes, then the delta S is greater than 0. Okay. So if it gives you more, that's more disorder. The total number of gas molecules goes down. So we've gone from, say, 3 moles of gas to 2 moles of gas. Then that delta S will be less than 0. If there is no net change in the number of gas molecules, then delta S could be either positive or negative, but it's going to be tiny. Okay? So that's just something to keep in mind. It's one of those things that you can use as sort of a reality check when we're looking at things. Okay. So questions so far? Okay. Now, when we talk about enthalpy and then entropy, we're talking about two different things that affect whether this thing is spontaneous or not. Both of these are factors in whether this is spontaneous or not. So if the enthalpy of a reaction is negative, if it's exothermic, heat is given off to the surroundings, then the disorder of the surrounding goes up, so the entropy goes up and is therefore positive. Because in that reaction, it's given off heat, so the entropy around it has gone up. The enthalpy of the reaction is positive if it's endothermic, heat is taken in from the surroundings. Then the disorder in the surroundings goes down, so entropy goes down. So the surroundings has gone down, but the system has probably gone up. Okay, so the delta S for the surroundings is related to the enthalpy of that system divided by T. Now, will you need to do any calculations with that? No, but it is a good reality check for you. Okay. The entropy of a perfect crystalline substance is 0 at the absolute 0 of temperature. Now, entropy above absolute 0 is always positive because there's molecular motion, so there's always some movement of those molecules. It's also positive at absolute 0 for material that's impure because there is disorder in the solid. Okay, so both of those are true. All right, so cool with that. So these two things are related. They're not the same, and we cannot use either one to determine spontaneity. So again, questions at this point? So based on what we've talked about so far, things that I might expect you to be able to do is to give me a rough definition of entropy. As you can probably guess, that definition does not need to be precise at all because we don't have a really great definition for it. I might ask you to explain what spontaneous means. So something that's spontaneous will happen in nature without any outside intervention. That's a typical thing that we state. All right. So something that can go on its own without anybody doing anything to it. And is it enough to know the enthalpy of a reaction to know if it's spontaneous? Is it enough to know the entropy? Well, let's consider the following reaction. So this is the Born-Haber process. We're taking N2 plus 3H2 going to 2NH3. And the delta H for that is negative. Okay? So it gives off heat to the surroundings. So it's an exothermic process. So it's exothermic. So that implies to us that that's a decent thing to do, right? Because it gives off energy to the surroundings. But from a logistical standpoint, before I calculate anything, I want to consider what happens when I take 4 moles of gas and go to 2 moles of gas. Which side is more disordered? It's the 4 moles that's more disordered, right? Because I have more ability to move when I have 4 moles of gas than when I make 2 moles of gas. So that implies to me that it's gotten more ordered as I've gone to the other side. And so is this really going to be a spontaneous process? Well, okay, let's consider that. So if I know that the absolute entropy values S at 238 for N2, H2, and NH3 are 192, 131, and 193 joules per Kelvin mole, respectively, I'm going to calculate delta S naught for the reaction. So my delta S naught for this is equal to the sum of the number of moles times the delta S naught for the products minus the sum of the number of moles times the delta S naught for my reactants, right? That's that equation that we've been talking about. So now I need to think about what are the values that I need to put in for this. So if I know that my N2 is 192, my H2, just making sure I get them in the right order, is 131, and my NH3 is 193, and those are all joules per Kelvin mole, then I can plug those in down here. So my product, I have 2 moles times the 193 joules per Kelvin mole minus the sum of my reactants. So I have 1 mole of N2 plus the 3 moles of my H2. Okay? And so I can do that happy math, and that should give me a value that I can calculate for this. So looking for my calculator, I take 2 times the 193, and I like to do this in 2 steps. So 386 joules per Kelvin minus the quantity of the 192 plus 3 times the 131, which is 585. And that gives me negative 199. And so as I and that's a negative. I swear I put that, but that's okay. That's a negative value. So because it's negative, then that means that this process does give me a negative change in entropy. I've gone from a less or more disordered system to a less disordered system. And so that is negative. But I also know that I can make this reaction happen. We make methane or ammonia all the time. So this happens. We just have to make it work. So that can be done. Okay. Now, because this is negative, again, it asks you to explain the sign of delta S 0. What I was looking for there is the fact that I've gone to a state that is less disordered. So that's what that means by that. It's like less disorder, which makes sense to me based on the number of moles that I have. Now, are there any questions about the calculation that I did or anything that I said about it? Okay. So that's the kind of thing that you're going to need to do with these values, is to be able to take them, put them into this equation, and calculate a delta S for them. All right. So other things that I would want us to be able to do is to use the standard thermodynamic values provided. Give me a second. Calculate the following. Please note please note these are listed in the order they appear in the chart. Now, the chart that I had is no longer available, so I apologize for that. So what I have for you guys is this link right here. I put it in the chat. And this link will take you to the ChemLibra text. And that reference is this table right here. These are all the standard thermodynamic values, so you can search through here and find the values that you need for those particular things. Now, if we're talking about the entropy values, those are these S values over here on the end, okay? So remember that that's what we're talking about. Our enthalpy values are these delta H, so we've talked about that already. This delta G in the middle, we haven't talked about yet. But this is the kind of thing that you'll see on the test is tables similar to this that will have delta H, delta G, and delta S in them. Okay, so remember that you want to look at these values over here in the far column for S when you're doing these calculations. All right, so hopefully you guys can all get to that link. If you can't get to that link, then that's going to be problematic in terms of calculating these things. But these are the things that I wanted you to calculate with that. So I was going to walk through the first one so that we could do that together, so you could see what it's like to go and find these things, assuming that I can find them with the tables that are here. Now, again, I unfortunately went to pull the table that I used before this morning and discovered that it was no longer available. So I cannot guarantee that all the values that I want are available in this table that we're looking at right here. So that's an unfortunate part of this, but hey, we'll see what we can find. So I'm going to use my Control F on this page because that means I can search for things. And of course, half of these are not going to be here. So, which is unfortunate. Now, notice that what we're looking at here, what it said at the top, is that these are quantities from the CRC for the 48th edition. So not everything is going to be here, which is unfortunate. We'll be able to work with the ones that are here, but that's about all we can do. So I do see BeOH2 is here. So we can probably work with this second one that's right here, the Be, the O2, and the H2. And so if I'm looking at the reaction from Be plus O2 plus H2 to make BeOH2. It's the reaction that I'm looking at for that. So energy of formation of this material from these components. All right. I have to assume that this is a solid because I wasn't told that. So I have to assume that that is a solid because it's the only value that I have. So I'm going to pull that value for the delta S, which is 45.5. Okay. And again, these are all joules per mole Kelvin. I then want to look for Be, which in its standard state should be a solid. And so this would be 9.5. This should be a gas, and this should be a gas. Because again, O2 and H2 both exist as gases in their native forms. So we want to look for O2, that is CO2. Next one. This is going to take me forever. There we go. So O2 by itself, 205.2. And if I wanted to find H2, need to get out of the carbons and into hydrogens. There we go. And that's 130.7 for H2. Now, do I provide you with these entire tables? No, I don't, because it's an enormous amount of material that you would have to look through to do it. That is what I used to do. And I found that that was exhausting for everyone. So that's why it's not done that way anymore. You will get an abbreviated table that will have probably 20 values in it, something along those lines for the exam. So you'll need to make sure that you find everything in the state that it needs to be in. And once you've found those values, then you should be able to plug them into that equation without much of an issue. Okay. So again, I would calculate this at delta S for formation, my product, and I have 1 mole of everything, so I'm not going to bother to multiply by the number of moles. So I'm getting a little bit lazy. So 45.5 joules per Kelvin for that reactant, or for my product, and then I'm going to subtract the total of the 9.5 plus the 205.2 plus the 130.7. Okay, and so that would be the total that I would get for that. And I've set that up for you. So does that make sense? So what I'd like to see us do is to choose at least 2 more of these. I'd like to have you guys take a look at what those values are. So it's up to you which ones you choose. But I think I'd like all of us to do the same ones. Let me see if I can find methanol on here. Yeah. So methanol, which is CH3. CH3OH. So going from a gas to a liquid, both of those values are there. So I think I'd like to have us do this one just so you can see what that looks like. And I'll leave that out for a little bit while I decide what else I would think we should look at. And I think probably this one, as long as I can find that value. So I'm going to go look for an H4F. And I don't see it. Bummer. Sucks. Not that one. Let me see if I can find rubidium chloride. I apologize for the fact that this was not available anymore, because it was when I looked a week ago. So RBCL we can definitely do. So this one here, you should be able to manage. So I think those two, as long as you can find those values and calculate those values, I think that would be a good exercise in that. Okay. So taking the values that I found in the table, I recorded those for each of these things. So RBCL was 95.9 joules per Kelvin mole. RB was 76.8 joules per Kelvin mole. Actually, that is probably the wrong one. I think I put the one for the solid, not the gas. I did, yep. Because it said to do it from the gas, and that is not the value that I pulled. So that would have been wrong on the test. I need to put that here. And that changed my math a little bit. So that gives me this value is -1 or -371.5. And then I did something weird with it, which may look weird anyway. And I divided that by 2. Now, the reason that I did that is because I asked for the heat of formation of RBCl. And when I wrote this reaction for this particular thing, in order to balance this, I had to form 2 moles of RBCl from the RB and the Cl2. So when I do the reaction as written, then this form is the heat of formation of 2 moles of RBCl. But I asked for the heat of formation of RBCl gas from this particular material. And actually, this is technically RBCl solid because that was the only one that was present. So that was what I did out because that's all I could get. But because I wanted the moles, the energy for 1 mole of that formation, again, we do this for 1 mole of that product, we have to divide that whole thing by 2 because we form 2 moles. Does that make sense? And this value is 185.75. And again, that's just because I have to do it for 1 mole of product rather than 2. And with my CH3 OH, the methanol, that was just the gas here minus the liquid here, which gave me the 131.1 joules per Kelvin. So does that make sense? Do we have any questions about what I did or why I did it?
Okay, I do have a question. Why not have the RBCL and have the whole equation then? Because you
What do you
only,
mean?
because like based on stoichiometry, you have 2 moles of the RBCL, but you're only looking for 1 mole of the RBCL. Why not just like not multiply by 2 to begin with when you have a 2 times 95.9, you know what I mean? But you
Because
like
what would I
actually
do
have the
with
whole thing.
the Cl2?
Oh, true. You have
Because
it.
the value right.
Okay.
So I can do the not multiply by 2 for everything as long as I remember to take half of that Cl2 value. So you
Okay.
can do it either way as long as the stoichiometry matches what you need. But
Okay.
because I had written the reaction to be 2 of those, then I needed to have those values match that.
Okay. That makes sense.
Yeah. And again, if you're doing that on a test and you want to make it for just 1 mole, that's fine. But then you need to show that this is 1 mole of RB solid plus half a mole of Cl2 going to 1 mole of RBCl for your balanced equation. And then your values need to match that, i.e., you need to have taken half of this value for Cl2 right here.
Gotcha.
And that
Thank you.
works. Yeah.
Okay.
Yeah.
Thanks.
Totally works. But But yes, that is one of those things where we have to pay attention to make sure that we've done what we needed to do in one place or the other. So, okay. So, are there any questions about that? Because literally, this is all you need to know about entropy is what it is and how to calculate these values, and then how to interpret the values that you have. So, for instance, I can tell you that 2 of these values are negative. That means that I have gone to a system that has less disorder than what I started with. So I've made something that was more ordered than what I started with. And that makes sense because here I have something that's more ordered than these 3 components. Here I have made something that is more ordered than these 2 components. In this last case, because I've gone from a liquid to a gas, then that one has more disorder in my product, which is why this value is positive. Okay. So I can interpret those values again based on the sign that they have. So that's the other thing that we're looking at is, do I have more disorder or less disorder based on what I've done? And that should make sense. Okay. So that's everything that we need to do with entropy. So are there any questions on entropy? So there is some more practice. I will definitely put up whatever values I can get from what is here. Okay. Now, there is an entropy in-class practice. I did put that up so that you guys can look at that, and it has the answers available to it. I will have all of the answers posted for these calculations shortly after class. So all the ones I didn't walk through. Now my question to you is this. Do you want to continue and talk about free energy today? So then you have more time to prepare for the exams, or do you not want to do that?
I mean, I'm game either way.
Does anybody not want to do that? You can raise your hand in the thing if you want. That's fine. I can do that. So I can
How
see
long
that.
would the other lesson be today?
About like this.
Okay.
Yeah. It's not much longer than this. And if it is, then we'll finish it out and pick it up on what's left on Friday.
When is the next test though? Next Monday?
So let me look because I actually didn't look it up this morning. I meant to, but I didn't. I think that the next test is supposed to open on Friday and close on Monday, and then the final opens right after that. Should we schedule? Oh yeah. Let's see. So I had the 20th slated for review, so 17th to the 20th is exam 3, which is this weekend. Yep. And then the 21st to the 24th is final. And again, I'm available any of that time if anyone wants to talk about anything.
Are
Okay.
we meeting
So-
next Monday to it says like a review?
Well, there was a review slated. So what we can do is if you guys want to meet, then I'm more than happy to meet with you. But we are not, I mean, if we finish material today and you don't need to talk to me again, you are not required to see me again. But if you want to talk to me, I'm more than happy to talk to any of you.
I mean, I feel like the review for the final would be kind of nice though. Because like I feel like the final for the last semester was just like it was so much, you know? Like I mean, I didn't even finish this up. Like I ran out of time.
Well, and okay, I'm gonna put it to you again. You're gonna hate this, but this one is designed exactly the same way.
Oh
So it is a very long test. It is designed to be too long for you to finish. I don't agree with that, but I have not won that battle. So the test is meant to be longer than you can finish in an hour and a half, and that is all the time that anybody gets for it. It is meant to force you to answer the questions you know how to answer.
man. Okay. Interesting. That's one, I guess that's one teaching technique.
It's a very old one. I will definitely say that. And I don't agree with it in any way, shape, or form. But I have not won that battle.
I mean, I feel like I would be down to meet up on Monday and like discuss some questions. If you like, but then we'll probably already take the test 3, and then you would know exactly where you are as far as you
Well,
are.
I won't have it graded by then because it doesn't close until Monday.
Right.
So
No, but at least you would like a person would know where they are standing. Because like I feel like after taking that test, you would know exactly where you would mess up, you know? I feel like you
maybe,
always,
maybe not.
yeah, true.
I mean, so in my opinion, people do exceptionally well on test 3 because it's all the same kind of calculation. So generally speaking, I find that people do exceptionally well on test 3.
Yeah. Also, I do have a question about the homework. I don't know if anyone's been
Yeah.
struggling with that, but I feel like Alex is like very particular about the sig figs. So like
Mm-hmm.
it keeps flagging you for like the wrong answers, but then you would like check the review and you would be like off by like 0.01 or something like that.
Yes.
And it doesn't like give you a chance to be like, are you sure this is what you're putting in? As in like, you know, like I think you should definitely check the sig figs, you know what I mean? It just accepts your answer. That's kind of ridiculous.
Well, okay, but it's been changed from the settings that it had for 110, where you were reminded about your sig figs, to you should know what your sig figs are.
Oh, you did that? Oh, okay.
Yeah, yeah, that is an intentional change. Yes, we do that. Um, there is, I mean, there is reason that you could argue for that you should get more points than you got, and if you want to argue that, then I can go and look at them. Absolutely, I can do that. So that is something I'm willing to look at because generally speaking, we only take like 1 point off of the tests for that. But your homework will not be perfect because of
Gotcha. Okay.
so. But yeah, if you want to have me go look at it, I can go look at it.
And you'll be posting like an exam 3 like review or practice exam.
Yes. So I hadn't made the one in Alex yet, which is why it's not posted yet. But yes, I'm doing that this afternoon so that will be posted today.
Okay, thank you.
And again, what I can do is we can talk through the rest of this today if we get through all of it today. And if you guys look at that and say, well, I don't know what to do with this, then let me know and we can absolutely meet on Friday or we can meet on Monday, either one. And if I have enough call for people wanting to do that, I will post that I'm going to meet with everybody and, you can come if you want. You can not come if you don't want to. So that's all this thing. How does that sound?
Sounds good.
Okay, awesome. So let's talk about free energy. So free energy is the last thing that we're going to be talking about. This is the last part of chapter 17. This is, we'll talk a little bit more about the second law of thermodynamics just in terms of how it fits into this part. We'll then talk about Gibbs free energy and the free energy and chemical equilibrium. So how those tie together. Because remember, way back when we talked about chemical equilibrium, and now they all tie together. So we're going to be able to tie that knot back and see how everything is connected. So let's get into this material. Now, when we talk about free energy, my main goal as a chemist is to be able to predict if a reaction will or will not occur under the conditions under which I'm trying to do it. I have to be able to consider both the enthalpy, that energy that's involved, and the entropy, the disorder that's involved, to determine whether or not this will actually happen. Okay, so we said, based on the second law of thermodynamics, that negative delta T over the delta S of the universe has to be less than 0 for a spontaneous reaction. And what that means is that the delta H for the system minus the T times the delta S for the system has to be less than 0 for a spontaneous reaction. So the combination of the enthalpy and the temperature times the entropy has to be less than 0 for this to be a spontaneous reaction. And we can rewrite that to delta G equals delta H minus T delta S. Okay, so the change in free energy, which is G. So again, G is my free energy. My H is my enthalpy. And my S is my entropy. This is the heat. This is the disorder. And we really term this as spontaneity for delta G. Okay, so those are those terms. So delta G, that spontaneity, is determined by the change in the enthalpy minus the temperature times the change in the entropy, where delta G is Gibbs free energy, or the energy available to do work. We can calculate that. One of the ways that we can calculate it is to calculate it exactly the same way that we've been talking about, with delta G equal to the sum of the number of moles of the delta G for the products minus the sum of the number of moles times the delta G for formation for the reactants. Okay, so that same equation that we've been talking about. All right, standard state for this, again, 1 atmosphere pressure for gases, pure liquids, pure solids, elements, delta G not F equals 0, and solution should be 1 molar concentrations. Okay, so everything needs to be pure when we're talking about these things. All right, so that's the heat of formations that we're talking about. All right, now, if that is the case, and that's what we're talking about, there are 4 different scenarios that I can look at when trying to determine if delta G is going to be spontaneous or less than 0. So I can have the case where my enthalpy is positive. I have to put in energy to make this happen. And if I have to put in energy, in which case it's my delta H is positive, that's these 2 rows that we're looking at here. Then I have one situation where my delta S is positive, so it becomes more disordered. And that reaction proceeds spontaneously at high temperature. So if the temperature is high enough, that will be a spontaneous reaction because I'm getting more disorder out of that system. So it's a good thing. Even if I have to put energy in to make it happen, getting the disorder out is good. So that will happen at high temperatures. At low temperatures, that won't be spontaneous because that factor, getting the entropy, will not be big enough. Okay. If, on the other hand, the delta H is positive, I have to put enthalpy energy into this thing to get it to happen, and the entropy is not favorable, i.e. it becomes less spontaneous, then delta G is always positive. That reaction is spontaneous in the reverse direction at all temperatures, but never in the forward direction. Never. And that's because neither the enthalpy nor the entropy is favorable. So as written, that thing will never happen on its own. So in this case, it will never happen as it's written. Reverse reaction always happens. Forward reaction never happens. If, on the other hand, we're talking about a situation where the enthalpy is favorable, so we're giving energy out to the surroundings, and so my delta H is negative, now we're talking about these 2 rows. Okay. Now, if it's favorable energy-wise to do this reaction, then the question becomes, is it favorable disorder-wise for this to happen? And if it's a positive delta S, then I get more disorder out of it. So it's favorable via energy, it's favorable via spontaneity, then that always happens. And it's always negative. So this always occurs. Never for that one, always for this one. And that's in the forward direction. If I reverse that reaction, it will never happen. Okay? So that's a situation where we can always have it happen. Now, the other one, where it's a favorable enthalpy, but it's a disfavorable entropy. So I like that Born-Haber process that we were talking about. This is one of those cases. So I gave off energy when I was talking about that process, but it was less favorable in terms of the entropy that we were looking at, because we were going from 4 moles to 2 moles, right? So this reaction reacts spontaneously at low temperatures. And that's because I'm not making good choices in terms of that spontaneity. So I have to have that spontaneity term be very small. And because it's multiplied by that temperature, it has to happen at low temperatures. Okay? So that's a situation where we have that kind of thing going on there. So we always have one case where it always happens, where delta G is always negative, and that's where the enthalpy is favorable, i.e. the enthalpy is negative, and the spontaneity is positive. So we get to be more disordered. We also have a case where it never happens, and that's when the enthalpy is not favorable, so it's an endothermic reaction, positive enthalpy, and a negative entropy. So we go from a more disordered system to a less disordered system. So those two are always like that. The other two cases are always temperature dependent. So it depends on what the temperature is, whether or not that's going to be spontaneous. And we can actually solve for, given those conditions, what temperature will make that spontaneous. So that is something we can do. Okay. Now, it's important that you understand this because you will get asked a lot of questions about this. So, when is it always favorable? When is it never favorable? When is it spontaneous at high temperatures? When is it spontaneous at low temperatures? So, I want to know what the signs are for delta H and delta S for those conditions. All right. So, that's something you'll get asked about. So, are there questions about that? Now, I understood that there was this table that told me this. I had to convince myself by doing 8,000 calculations that was actually true. I hope that it doesn't take you that long to figure out that this is actually the way that it works. So, okay. So there are rules for when things will happen, when things won't happen. It's the combination of those two factors that will determine whether it's spontaneous or not. Okay? Now, having said that, and knowing that we have this equation for delta G equals delta H minus T delta S, which, by the way, is on this handout. Where did it go? I know it's here. It's right here. So delta G equals delta H minus T delta S. So that will always be present for you, just so you will be able to use it. And knowing that that is the case, we can determine at what temperatures, if any, these things can happen. Now, all of these here were based on the calculations that we did in the previous lecture. So we were able to do the one for the RBCL solid, and we were able to do the one for this one here. So both of those we were able to do. And so we can go back to the values that we calculated there. And from what I remember, this had a negative delta S. And this one has a positive delta S. Okay. And we talked about the fact that those were what they were because we were making more order out of this system and less order out of this system. Okay. So if that is correct, and based on the values that we calculated, which I'm going to go collect because I forgot to write them down. So give me 2 seconds and I will pull it up. So my RBCL, we had negative 185.75 for 1 mole of that. Give me 2 seconds. I need to write something. I have no pen on my desk. I apologize. And my methanol was 131.1 joules per Kelvin. So those were the delta S values that we calculated here. Now, we can use the tables that we had pulled up to be able to look at the delta H values for those same processes. So if I were to go back to this right here, this guy, and let's go back up for methanol. RB, where is RB? So for right here, we have our RB, and it asked for gas plus Cl2 gas going to RbCl solid, because that was the only thing we could make based on these numbers. The delta H for the RB solid, there's no value for that. So it's 0. I mean, it's supposed to be like that. 80.9 for the gas for the RB. My RbCl solid is negative 435.4, which I can use directly. Give me 2 seconds. I'll pull the other one. Yeah, that one's 0 as well. And then our methanol values. Okay. So I wrote down the values that I found in the table for those delta H values. Okay, because I wanted to be able to calculate delta H for these processes, because I need to have delta H and delta S to be able to calculate delta G. All right. So I want to be able to determine at what temperature, if any, the reaction will become spontaneous. And so what I know is that when it becomes spontaneous, it goes from positive to negative. So we're looking for where that delta G becomes 0. Okay. If delta G is 0, my reaction or my equation is delta G equals delta H minus T delta S, and we're looking for the place where this becomes 0, then that means that 0 is equal to delta H minus T delta S. And so I can solve for when delta H is equal to negative or positive, because I need to pull it to the other side. So delta H, I pull that over there. So delta H is equal to T over delta S. That's where that sign change will happen mathematically. So that's what I'm going to solve for, is where that happens. And so I need a delta H for that and an S for that to be able to solve for T. Does that make sense?
Why is it the T over S though? I thought it was a T times delta S. Isn't that the
Why am I
formula?
writing it? Well, yeah, because I wrote it wrong.
Oh, okay.
And once I wrote it wrong, I kept writing it wrong. I apologize. That's my fault.
Okay. Sorry.
No, that's my fault. And I apologize for doing it. And thank you for helping me find it. That's what it should look like. And so if I wanted to find that, I can solve for that T. That's equal to delta H over delta S. Better? I hope so.
Perfect.
Yeah. So now I can solve for that. But again, I need to have a delta H value to do that. So now I have the delta S values for both of these equations because I wrote them down. So the delta S on this one was negative 187.5. That's what we calculated. And this one was 131.1. And again, this is joules per Kelvin. This is joules per Kelvin. Okay. So if I were to calculate delta H for both of these reactions, if I want delta H is equal to the sum of the number of moles times the delta H, not F for the products. Just as a reminder, sum the number of moles times the delta H, not F for the reactants. And so for my RB case, I'm looking at the number of moles. And again, I have 2 here and 2 there. So I have 2 times the negative 435.4. And these are kilojoules per mole. Minus 2 times the 80.9. And again, this is moles and this is kilojoules per mole, because that's what those units are in that table. So remember, we had talked about that, mentioned it. So all of these guys, for these two, delta H and delta G, are in kilojoules. This one is in joules. So we have to be aware of that. So calculating this value here, and of course, if I want it for 1 mole of this thing, it's going to be 1/2 of this value because I'm calculating for 2 moles of Cl2. So I could not multiply both of these by 2 if I wanted to do that. And I end up with a negative delta G for the RBCl for 1 mole of 124.44 kilojoules. And again, that's for 1 mole of that product. All right, if I do it for the reaction for the CH3, this OH, the methanol, that one is going to be equal to the negative 201.0 minus the negative 239.2. Two 1.0 minus the 239. And I get negative 440.2. And again, that's kilojoules. So both of those answers are in kilojoules. So if I plug that into this equation that I have, this one that I solved for right here, T is equal to the delta H that I solved for, the negative 124.44 kilojoules, divided by my delta S, which again for this was negative 182.5 joules. And over here I have T is equal to the negative 440.2 kilojoules divided by that 131.1 joules. Okay. Obviously, that is the right setup, but I have to do some conversions before that will work. Okay. I either have to convert one of these, i.e. this one to joules, or this one to kilojoules. Either one is fine. Okay. Since this is in joules per Kelvin, the units on whichever way I convert it, that unit will be Kelvin by the time I'm done. But I have to convert one of them before I do it. Okay. So I tend to do it into joules. It's just tends to be the way I do it. So I'll take the 124.4 and I will multiply that by 1,000. And so I would end up with 124,400 joules over, and it's negative 182.5 joules per Kelvin. And of course, if I were to do the same thing down here, multiply that 440.2, because yes, I am that bad. And that one is negative over the 131.1 joules per Kelvin. So then I can do the math. And if I do that, I will end up with the negative 124,400 divided by the negative 182.5. And that gives me 681.64 Kelvin. Okay. So that's the temperature at which that would become spontaneous. Right? If we were to look at the other one, and we have that negative 440,200 divided by the 131.5, and I end up with this negative value, right? And there's change out there. I'm going to put this as 5.3 because I've got 2 decimal places, so I'm just going to leave it at 2 decimal places. Not really paying attention to sig figs at this point. And my question becomes, does that make reasonable sense to you? Because one of them makes reasonable sense to me. The other one doesn't. What do I know about temperature in Kelvin?
It can be negative.
Correct. So it can't be negative. And so what that tells me is that there is no temperature at which this particular processes would change from one to the other. Okay. So there is no place where this changes from spontaneous to non-spontaneous, depending on which one it was to begin with. And of course, I haven't really paid attention to whether it should be spontaneous or non-spontaneous. Looking at the energy that's involved, if my enthalpy is negative and my entropy is positive, is it ever non-spontaneous?
No.
No. And that makes perfect sense given what I found. Because if it's never going to be non-spontaneous, there's no temperature at which it can turn non-spontaneous. So because of the fact that this has a negative delta H and a positive delta S, this is always spontaneous. And so if I was paying a little bit of attention, I wouldn't have had to calculate that. But I wanted to show you that that's the actual value that you'll get. So if you're not really paying attention to it, you'll end up with this negative temperature, which makes no physical sense. Okay? So that's why this exercise was here, was to show you that that's exactly what you would see. All right? So this tells you that this particular reaction will never become non-spontaneous. It's always spontaneous. On the other hand, this reaction over here, where we're talking about it having an negative delta H, which is favorable, but a negative delta S, then I need to be at this temperature to make this happen. So there is a temperature change at which that will become spontaneous and below which it will not be. So this only happens at above certain temperatures. Okay?
Yeah.
Does that make sense? So again, that is something that you could be asked for. What is the temperature which has become spontaneous? If you were to remember the rules that you have, you would know that this one, we don't have to solve for that. And I don't expect you to solve for this. If you can show me that this is negative and this is positive, I don't expect you to solve this. You don't have to. But if you decided to go ahead and solve it without thinking about that, or just do it because you wanted to show it, either one, then you would end up with this negative value, which you cannot have. And so you need to say, hey, it can't be a negative Kelvin, so this can never happen. Okay? So that's how that works.
I do have a question. So from that original reaction, I mean the equation, the delta G is delta H minus T delta S. You just assume
Correct.
that delta G would be 0, but I feel like it's always spontaneous when delta G is less than a 0.
That's correct. We're looking at the point for which it changes spontaneity. That's why I asked you. Determine at what temperatures, if any, the reaction will become spontaneous.
Okay. Okay.
So I'm looking for where is that point that it can change from spontaneous to non-spontaneous. That's what I'm looking for.
Okay. Thank you.
Yep, absolutely. Okay. So that's one of the practical ways that we talk about this, because you may be presented with a reaction where they say, okay, we want you to do this, and it's favorable in one way, but not favorable in the other way. And so you have to figure out, is there a temperature at which I can run this reaction so that I can make it happen? That is a very common thing for us to have to solve for in the lab. So that's why one of the things that we wanted to talk about was how do we solve for that temperature? Okay. Now again, once I have values for these two, assuming I can find them with the information that's available, I will post those two as well. Okay. But I talked about the two that I actually cared the most about. So. And I said at one point that I could take the value as written, and in theory, I would be able to use this value if I was forming this from the solid and the gas. So if I were making it from things that were in their standard states, I would be able to do that. But because this is in the gas phase and not in the solid phase, I can't just use this value, because it has to be modified by the fact that I had to put this into the gas phase first. So that was why that I thought that maybe I could get away with that, but I can't, because I'm in the gas phase and not in the solid phase. Okay. So other things that we want to be able to calculate delta G's for. So I would like to calculate a delta G for the things that we calculated them for the last time. So this guy right here, not that one, sorry, wrong one, this one. Doing this now that we've done this from the sense of using the tabulated values, okay? And we're going to do this at 45 degrees C, right? So we have our tabulated values here for those things. Delta G is this thing in the middle, so we can use these tabulated values to calculate those in the same way, as long as we know what that temperature is. And again, I said I wanted to do this at 45 degrees C. So when we calculate what that temperature is in Kelvin, we'll take our 45, 45 plus 273.15, and that would give us 318.15. So is the temperature we want to run this at. So calculating delta G. So we're going to calculate that based on what we know for normal things. So we'll calculate the value at standard. That's what I'd like you to do, is calculate the value at standard. So delta G, not F, at 25 degrees C. And then we'll calculate it at 45 degrees C. And there are two different ways that you have to do that. So we can use the tabulated values of delta G for this one. With this one, we're going to have to calculate delta G based on delta H minus T delta S. And we have those delta H values and the delta S values. It's not T over delta S. Why do I keep writing T delta S? And so we have delta H and delta S for that. So we can calculate that at a different temperature using that. Does that make sense? So let's walk through the first one. So we'll talk about the methanol gas going from liquid methanol. Okay, so we'll go back and look at our CH3OH values. And again, for our liquid, we have negative 166.6 is the value for the liquid. And then the value for the gas is negative 162.3. Yes. And so those are the delta G values that I got from the table. So I can calculate delta G for the formation is equal to the delta G for my reactant, for my product, 162.3 kilojoules per mole, and it's 1 mole, so I can get rid of the mole there. And then I subtract the negative 166.6 for the liquid. Okay, so those are the two values that I have. I can do that subtraction. Negative, darn it. I always forget I can't use that negative key to do that. 162.3. And then I'm going to subtract the negative 166.6. Wrong thing. Sorry, hit the wrong key. And I should end up with a positive number, which is not very big, which is 4.3. So that's how much energy it takes under standard conditions to do this. All right. So that's my standard for this. If I want to calculate delta G, which is not standard, so it would be a delta G F, but not with the little circle because it's not standard because it's not 25 degrees. That would be equal to the delta H minus the T delta S, which my delta H for this we calculated to be, there you go, negative 440.2 kilojoules. Minus that temperature, the 318.15, times the delta S, which we calculated for this one to be negative 187.5 joules per Kelvin. And so I can do the calculation with the temperature to do 318.15. Oh, for crying out loud. 318.15. I can multiply that times the negative 187. And that's not the right thing. 0.5. And so I end up with this value, and that's in joules. So then I can divide that by 1,000 to get that into kilojoules. And that gives me equal to the negative 440.2 kilojoules minus the 59 point. It's negative 59.653125 because I'm not rounding it, and that's in kilojoules. And so I would take negative 440.2 minus that value that I just calculated. And that gives me negative 380.54. And I haven't rounded this. 875. Now, looking at, just so we can talk about it for a second, looking at sig figs, I have 4 significant digits on my value for delta H. I end up with 2, 3, 4, 5, 4 significant digits for my value for delta S, and that's because of the joules per Kelvin that has 4 sig figs. So when I do the subtraction, I would end up with 1 decimal place that is significant for this, because when we do the subtraction, it's the number of decimal places on the least significant digit. So this one only has 1 decimal place, so my answer should only have 1 decimal place. And so this should be reported as negative 380.5, because it's 5.4, so kilojoules. So again, when you do that subtraction, remember that your rules are not based on the total number of significant digits, but based on where the last number is significant. So the number of decimal places that the least significant number has. So rules change a little bit. Okay. So does that make sense for how I did that? So the unit conversion that needs to happen with the delta S and the rounding that was done at the end. Yeah. So that's how we calculate those 2 values for the methanol. Now, if we wanted to do the RBCl gas from RB gas and Cl2 gas, my standard conditions, I would need to look up those values. So let's find those. So looking at the RB gas, my delta G for the RB gas, I have 53.1 from, oh, that's actually RB gas, not RBCl. And my Cl2, and actually I need the RB, this one has to be the solid because that's the only one I have. And this one is negative 407.8. So those are the delta G values. Now let me go find that Cl2 again. Yeah. And my delta G on that is 0, which I was pretty sure it was, but I wanted to make sure. So 0.0 there. So if we're calculating that delta G under standard conditions for this, that's going to be equal to my products, which is a negative 407.8, and that's kilojoules. Since there's 1 mole of that, I've done that multiplication already to get rid of that per mole that goes there, minus my reactants. So the 53.1, and again, depending on how you balance this, you're either going to need to multiply this one and this one by 2, or take this one and divide it by 2. But since I don't want to have to divide anything, I'm not going to multiply anything, because dividing this by 2 gives me 0. So I'm just going to leave it that way. If that makes sense, great. If it doesn't, then we can chat about that. and then plus the 0.0. So that is how I would calculate that value. So I have the negative 407.8 minus the negative, well, it's not negative, so never mind, minus 53.1. And that gives me, under standard conditions, delta G naught F is equal to negative 460.9 kilojoules. So again, at 25 degrees, that's my standard free energy of formation for that material. Okay. So that's what we're looking at standard conditions, 25. If I were to calculate it for 45 degrees, I would then be looking at delta GF equal to that delta H minus T delta S. My delta H for this, I put negative 124.44, negative 124.44. So negative 124.44 kilojoules minus that temperature, the 318.15, times the delta S that we calculated for this, which delta S for this particular thing was 187.5. Did I use that? Oh, I used the wrong value. Holy mackerel. So when I did this calculation right here, I used the wrong value. I did that for the delta S for the RB and not for the methanol, which should have been 131.1. So, oops, that is bad. Let me write that down. And I will fix that. Number in just a second. I apologize. I'm so sorry. This is what happens when I don't write stuff down the way I should. So 124.44, again, that is, yep, those are RBCL, and this value is RBCL. So yes. And this is one of the things that I as a student ran into, was when I was not writing things down in systematic ways, I would do two calculations for delta G, delta S, whatever, and then try to calculate, well, so I do delta H, then delta S, and then try to do delta G, and I would occasionally confuse them. So being a little more systematic about doing it tends to help. Hopefully that's not something you'll run into on a test for this, but you'll see that in a lot of the homeworks, you're being asked to calculate these things for multiple things. So make sure that you keep them together the way they're supposed to be. I apologize for that. So if I were to do that, this calculation right here, so the 124.44 negative 124.44 kilojoules minus the quantity 318.15 times the 187.5. And of course, that is a negative value, so I'm going to go back and put that in because I forgot it. That way my sign will be correct. And that I need to divide that by 1,000 because this is in joules. So I need to make sure it's in kilojoules when I do that entire calculation. So doing all of that at once, I end up with negative 64.78. And darn it. So I ended up with, where'd my calculator go? Negative 64 point. And again, looking at number of sig figs, that's 4 sig figs there. That is 5 sig figs, so that should be, that's 1 decimal place. That's 2 decimal places, so this should be 1 decimal place. So 64.8. And that's kilojoules. And I will recalculate this number down here at the bottom because I messed that up. So, does anybody have any questions? So, fixing that other value. So, does anybody have any questions about that? So, as we've discussed before, we can use the tabulated values to calculate a delta G naught F, the standard free energy of formation, using the tabulated values. If we're not under standard conditions, i.e., our temperature is different, then we do the calculation based on the delta H, the delta S, and the temperature. Okay, so that's what we've done with this, is the delta H, the delta S, and that temperature. So make sure that we have that temperature consideration taken into this to see if it's spontaneous or not. Okay. So we can calculate a number of things. What I was asking you to do here was to calculate a number of different things. These 2 were entropies for things that we've calculated previously, or 3. The rest of these, I meant these for just be standard delta G values for these, for things that we had already looked at. Now again, some of these may be present in the table that you have available, some may not. For those that are not, I will go and find the values that you need so that you can practice with these, because I thought they were interesting reactions, so I will go and find those values for you. So I will find tabulated values for you. Delta G, delta H, delta S, so that you can calculate those things. Because I thought they were interesting calculations to do. Some of them just based on the stoichiometry that you're looking at there. Some of them based on what some of these other things are. So, and I will make sure that all of that is posted so that you can look at what are those values, how do we calculate those things. Okay. And I promise that these are harder than what you'll see on the test. For the majority of them, anyway. So When a reaction is no longer favorable, the sign of delta G changes from negative to positive. We talked about that. We can set that so that delta G equals 0, then delta H equals T delta S, and we can solve for that T. So we can solve for that T as we discussed. So you may be asked what temperature at which these things become spontaneous or non-spontaneous based on the conditions that we're looking at. So the typical way that I would have you do something along these lines is I would present you with a reaction that we wanted to look at. I would ask you to calculate the enthalpy, so delta H. I would ask you to calculate the entropy, delta S. I would ask you to calculate the free energy, delta G. And I would typically do that for formation based on tabulated values. And then I would ask you to calculate, so this would be this kind of delta G. And then I would ask you to calculate a delta G at a different temperature. And then for a reaction where it is favorable for enthalpy or entropy, but not both, I could then ask you at what temperature does this become spontaneous? So I could ask you at what T. Now, knowing that this is the same equation for all of them, what I would need to see from you guys is that you understand that it's the same equation for all. So you can write one of the equations and say this applies to all for delta H, delta G, delta S. All of them have this format. And then you can just do the mathematics in your calculators. It's important that you show me the values that we used. So similar to what I've done where I've written them above the equation or whatever, that kind of thing, so that I can see the values that you're using, because it may be that you've accidentally chosen the wrong value. If you accidentally choose the wrong value, then that means that your answer will be wrong. But if I don't see the values that you chose, then I don't know why it's wrong. So I need to see where you picked, what values you picked to do these calculations. Because if I don't see that, then I just have a wrong answer, and I don't know where you went wrong with that. Getting a wrong answer with no reasoning for it is a very different grading than if I know that you picked the wrong value. Picking the wrong value is like a 2-point mistake. Getting the wrong answer is like an 8-point mistake. Okay, so very different thing. So it's important that I can see, hey, this, delta whatever, and I usually do this as delta X is equal to the sum of N times the delta X for the products minus the sum times the M for the delta X for the reactants. That's the format of all those equations for delta H, delta S, and delta G. So this is one of the things that I used to write so that I could show that I knew what the reaction was. And then I would write the reaction that I was trying to calculate it for. So if I was trying to do it for like the Born-Haber process, so N2 plus 3H2 goes to 2NH3, then I would make myself a table underneath it for delta H, delta G, delta S, list the values that I'd chosen for each of those things. And then that way you could see the values that I'd chosen so that then you would know what those calculations were supposed to look like. And as long as I can see something like that, then I know what you were trying to do. Okay. So that's a sufficient way for me to be able to see what you're attempting to do. So I would need to see the result for your delta H value, for the delta S value, for the delta G standard value, and then I would need to see that set up for the delta G at whatever temperature. And for the T where it became spontaneous. Okay, and I will show you one of those on the setup for the test. So I will show you exactly what I'm expecting for that cut. Does that make sense? So a little more practice here, finding that T at which that happens. I will post those because we did 2 of those. So I will make sure that I post that. I wanted to talk just a tiny bit about phase transitions and free energy. Now, because the temperature is constant during phase change, free energy is 0 because the system is at equilibrium. It is. But there's a large change in spontaneity in these processes. So to go from more ordered to less ordered, it's a negative entropy. It's less ordered and thus is favorable. So if I were to go from solid to liquid, that's a favorable thing. And we can measure the molar heat of the change, delta S, equal to that change in enthalpy divided by T. Okay. To go from less ordered to more ordered, it's a positive value. So that will be the opposite in sign, but the same in size. Right? So that is something that can be done. I'm not going to expect you to do this, but it's important that you understand that that is true. Okay, so that's how we measure the change in the entropy at those phase transitions. Okay. Questions about that? Like I said, I will not make you do this on a test, but I will post how this is done for 2. Okay. Unless you want to see them now. Okay. Now, once upon a time, once a very long time ago, we talked about chemical equilibrium. Remember, we talked about K, and we talked about how spontaneous a reaction is based on the value of K. If it's a very large K, then as written, we prefer products over reactants. If the K is approximately equal to 1, then we have no real, it favors both reactions and products. And if K is less than 1, then we favor products or favor reactions over products. Okay. Now, if that's true, then we know that there are some reactions that like to be forward, some that like to be backwards, that kind of thing. And there is a relationship between the free energy under non-standard conditions and the standard free energy. Okay. So just as we did with our electrode potentials, remember we could do a correction if we weren't under standard conditions. We can do the same thing for delta G, and it looks very much the same way. So delta G is equal to the standard free energy plus the R times the temperature times the natural log of Q, where those conditions are based on whatever concentrations we have. So we can do the same kind of thing for delta G that we did for delta E, okay, for that energy, or electromotive force. So a large negative value of delta G 0 will tend to make delta G also negative. The reaction will proceed from left to right until a significant amount of product is formed. Large positive delta G 0 will tend to make delta G also positive. Thus, the net reaction will proceed from right to left until a significant amount of reactant has been formed. And at equilibrium, delta G is equal to 0. Q is equal to K, and so delta G for the standard is equal to the minus RT ln of K. So there is a relationship between the standard standard free energy and that equilibrium constant. Okay, and this is the relationship that we have. So we know that if we have a K that's very large, the natural log of that is positive, and so delta G is negative. Okay, so products are favored over reactants at equilibrium. Right? If it's approximately 1, then the natural log of K is 0. And so our G is 0 because the K is exactly where it's supposed to be. Right? So, and if our K is less than 1, then the natural log of K is negative, and that means that our delta G is positive. Okay? And so reactants are favored over products at equilibrium because of that, the way that we've written that reaction. Okay? So there is that relationship that exists between those things. This reaction or this equation is present on the test. It's the exam handout. So is this one. Okay, so both of those are there if you needed them. I try not to ask a lot about that, but they are present. Okay, so you can look at those. So they are in those exam handouts. Okay, so there is a connection between those two. We talked about this briefly when we talked about the relationship between delta G, K, and E at the end of the redox section when we talked about that. So here I'm asking you to calculate some free energy values that, and therefore calculating K based on them. Now we can calculate that K. So we did this one here. We calculated a delta G for this, and the delta G that we calculated for that methanol reaction, if we go back and look at that, the delta G for our methanol reaction is the one that we calculated here. Right? Is that the right one? No. This is the RBCl and this is methanol. Just want to put those down. Give me a second. Oh, I don't have to keep flipping to it. So if those are the values that we calculated there for delta G, then we can use this equation to solve for K. So our delta G for the methanol reaction, we calculated as negative 481.9 kilojoules. Okay. That was the number that we calculated for delta G. And the reaction that we have, that actual equation, is delta G naught is equal to negative RT ln of K. Okay. So right. So knowing that that's the case, and knowing that R under these conditions, which is in the exam handout, I'll show you that value. R is listed right here is 8.31446 joules per Kelvin mole. So I have that R value, I have my delta G value. So if I have delta G equals negative 481.9 kilojoules, that's equal to negative 8.31446 joules per Kelvin. The temperature that we're looking at under standard conditions is 298. That's 25 degrees C. So that's 298.15 Kelvin. And then the natural log of K. And so I can solve this to get the natural log of K. And that's going to be equal to that negative 481.9 kilojoules divided by the 8.314 times 298. So I'm going to do that math. 298.15 times 8.31446. Now that is in joules, so I'm going to divide that to get it into kilojoules. And of course, that's a negative value because of this negative sign right here. So that is negative 2.47895 249 because I'm round any of that. And that, of course, is in kilojoules also. So I can take and divide that negative 481.9 divided by this answer that I calculated here, which of course is negative, and I'll fix that in just a second because I forgot to put that in. If I don't get my signs right, then it doesn't work well. And so that means that the natural log of k is equal to 194 and change. Okay, I'm not going to write any of that down. If I wanted to get out of the natural log of k, I have to raise this to the e power. So I go e natural log of k is equal to e 194 point and all of that stuff. And so that will leave me with k on this side. That's how we do the inverse of that natural log. And so I would take my e. And then put in this lovely number that I have here. And that gives you the value of k. 2.66. And looking at sig figs, based on what I have 4 sig figs for the delta G that I calculated. I have more than 4 sig figs in both the constants that I have, so, and I really shouldn't determine this, so it should end up being 4 sig figs that I report here. So that would be the value that I would report. So, does that make sense? So that is how we would go between delta G and K. So if I have delta G, I can get K. If I have K, I can get delta G. All right. And the rest of these are sample questions that I would be willing and or able to ask you based on what we have done. And I'm happy to hang in. Let me just make sure there's nothing else in here. Nope, this is all sample questions that I would be willing to ask based on what we've got. So I am more than willing to hang out, talk about any of these sample questions. I will definitely post all of this. If there is anything that is unclear to you, let me know. Send me an email, say either this is the question I have, or I want to talk to you either Friday, Monday, whatever. It's up to you. So, and if I get enough people, probably more than 2 people, 2 or more, that want to talk either Friday or Monday, then I will be happy to do that. So any questions moving forward? I will do everything I can to make sure that your grades are up to date with all of the surveys, the lab materials, and exam 2 tonight. I'll do everything I can to make sure that's done before I go to bed tonight. So
I do have a question about the surveys. I think I've been submitting
yes.
them. I've been submitting them to like that survey thing, but I haven't done like a screenshot or something like that.
And as I stated, I will get to it eventually.
Yeah,
But
okay. I was just saying,
yeah.
yeah. And then there was
It,
one
I,
that you said
go
you were
ahead.
gonna postpone, but it closed off anyways. I think there was like the
So
last two.
the redox one I had reopened for a couple of people. If you need me to, and I will go in and reopen the redox one. The
Yeah,
redox in the activity series.
because that's the one. I think it's that one I'm missing, and I just couldn't even like put it in there. It says because it says not submitted, but I'm like I know I've submitted it.
Well, I will take a look at it and see what's going on, and I will contact you if I need anything. How's that?
Perfect. Yeah, I think it's the Redux and Activity series. I think that's the one. Or maybe
I will definitely open up both of those for everybody just to make sure that everybody's got access to that, because I know that there was some. I didn't get them reopened or extended as I should have, so I'll make sure that that's done. But if there's anything I need from you, Dennis, I'll let you know.
Perfect. Thank you.
Anything else?
Nope. Thank you so much.
All right, guys. Well, it's been a great pleasure. Let me know if you need anything. I am not cutting myself off from you guys in any way, shape, or form. I just want to give you the time that you need to be able to do things that you might need to do. If there's any questions of any kind about like stuff in Alex that you want me to look at, stuff that hasn't been graded yet, anything like that, let me know and I will be happy to answer. So, like I said, I will get everything graded today if I can. And if not, I will let you know what's outstanding and what will get done tomorrow.
Sounds good. Yeah, so do we have a class on Friday or no?
If I hear from anybody who wants to meet on Friday, I will post that we're going to meet. If I don't hear from anybody, then I'm not going to be here.
Okay.
I mean, if none of you want to be here, then I don't see the point in making us all be here.
Oh, that's true.
But if anybody wants to meet, I'm more than happy to do so. Just let me know.
Okay. Sounds good. So that means we're pretty much done with everything.
That is correct.
Oh, wow. That was a quick one. All right. Well, it's been amazing. Yeah, the one I'm missing is the buffers. Buffers. I know I submitted that one. Okay, never mind. Okay. Well,
I'll look at it.
let me know if
I'll
you
look
need
at it.
I mean, okay. Thank you so
I will.
much.
Thanks.
Yes, ma'am. Have a good one.